Our second talk today is by Michael Kass of PIXAR, who is this year's Computer Graphics Achievement Award winner. Michael.
I'd like to thank the committee for giving me this extraordinary award. As you probably know, this is a new format that we're experimenting with this year, these award talks. And if they're successful, they're probably the beginning of a new SIGGRAPH tradition. Otherwise, we'll probably try a different experiment next year. The committee cited a wide variety of my work in giving me this award, and some of it is absolutely mainstream graphics. For example, the work that I did with Ned Green on approximate and hierarchical visibility. It's difficult to name a problem in graphics that's more central than figuring out which surfaces are visible. At the same time, the work that I've done, which has probably been the most influential and the work of which I'm most proud, is work which, at least at the time, was considered on the edge of what was graphics. You could look at it and say, is this graphics at all? For example, about 20 years ago, Andy Witkin and I wrote a paper called Space-Time Constraints, where we looked at computing motion which is as physically realistic as possible while simultaneously obeying a set of constraints provided by an animator. At the time, this work was rather controversial. It just barely snuck into the conference. Some of the reviewers looked at it and they said, well, this isn't graphics, this is control theory. It should go to a control theory conference. Since that time, there have been dozens of SIGGRAPH papers which have used this basic framework, extended it, and gone in some very, very interesting new ways. And with benefit of hindsight, we can look at it and say, yes, definitely. Now we can say this is graphics. I'll give you a second example, again from about 20 years ago. This is work I did with Dimitri Terzopoulos and Andrew Witkin, where we introduced a notion we called snakes. These are what we called active contour models, contours that try to remain as smooth as possible and which are attracted to interesting image features like edges, lines, texture boundaries, things like that. If the snake doesn't go to the particular edge or line or feature that you're interested in, you can grab it, pull on it with the mouse, and bring it near the feature that you intend. And it will, through its local optimization, hopefully come and track that feature fairly accurately. Well, at the time we introduced this paper, graphics people looked at it and said, well, this is a paper about analysis, not synthesis. That makes it computer vision. Computer vision people looked at this and said, this is an interactive technique. Vision should be automatic. That makes it graphics. Well, now, with benefit of hindsight, both fields have embraced this work, and we can say, well, it's both. It's graphics and it's vision. Both of these fields have gotten a lot closer together. Here's a third example. This is work that I did with Gavin Miller, where we used shallow water equations to create a film that we showed in the SIGGRAPH film show. And the paper that is based on this work, people looked at it, some graphics people looked at it and said, well, gee, this isn't graphics. This is fluid dynamics. You should send this to a fluid dynamics conference. All of which raises the question, what is graphics anyway? Is graphics just making pictures with computers? Just like we can't say that anytime you use a computer, you're doing computer science, we need to be more specific than this. Well, what could we do? Could we go back to what the great people at the beginning of our field might have thought? The field has progressed in a lot of ways that they could never have anticipated. So maybe we should look at a textbook. But the people who write the textbooks will be the first to tell you that the textbooks follow the field, not the other way around. So what is graphics, after all? I'll say that graphics is what we define through the process by which SIGGRAPH solicits material and selects the material out of that which it accepts and presents at this conference. And you might think, well, graphics has now been around long enough that we should know what it is, or at least we know it when we see it. But I would argue that it's very important to recognize that this is an ongoing process by which we collectively decide what we want to include, what we want to encourage, and by doing so, hopefully, we keep the field vibrant. And it's a really current topic. It never goes away. I was on the SIGGRAPH paper committee this year, and one of the people on the committee wrote in a review about a paper, this paper might be better received at an image processing conference. And I have to say that from my perspective, that's exactly backwards. We need to say, no, on the other hand, if we accept provocative, interesting, exciting image processing papers at this conference, then all of those people will have a reason to come to SIGGRAPH. And that will keep our field as vibrant as it possibly can be. The particular issue of image processing has a personal relevance. I'm now working on some painterly rendering techniques, some of which are entirely image-based. So image processing, which creates strokes that manage to stick to the object so that as the objects move around, the strokes look like they're painted and moving correctly. It does this without using optic flow, and it does this while maintaining good temporal coherence. This is some work with Justin Solomon at Stanford University. And here you have a clip. At the top is an original clip from Ratatouille, and at the bottom you see it processed through our algorithm. And looks perhaps a bit like a woodcut, but the strokes are stuck to the objects, moving nicely with it, and not jittering around as something that would look like if it was painted by hand. So now I'm going to give you an example that's even further off. And this is an experience I had of building a WALL-E robot. And I'm going to ask you to think about whether this is graphics or not, or whether it should be. And the genesis of this project is that at some point, the marketing departments at Disney and PIXAR realized that we didn't really have sufficient celebrity voices for the film to adequately promote the film on talk shows and the like. And someone said, well, gee, what if, we have experience with animatronics, what if we actually built a real robot? And very late in the game, with about 6 months before the release of the movie, a decision was made, yes, to try to build a real WALL-E robot. So we had a mad dash trying to create what turned out to be a 480-pound teleoperated animatronic character. And of course, there was a huge crew of people that were involved in building this, a large crew at PIXAR. These were the people that really spent a lot of time working directly on the project. There was a large team from Imagineering. These are some of their names. In addition, there were a collection of people that worked on the WALL-E film that helped as WALL-E advisors, trying to keep us, make sure that the robot actually was a good embodiment of the character in the film. And in addition to all these groups, there was also a large group at Function Engineering in Palo Alto, which did a lot of the mechanical design. So the first thing that we did is went through and kind of analyzed the character, tried to figure out how we could simplify him to the point where we could actually build a real robot. We settled on 23 degrees of freedom, so WALL-E has 23 separate motors. And these are some of the early CAD models that were put together by Function. And then those models, some of the pieces from those models were fabricated, and we created a prototype of all the different parts. This is the head and neck assembly, so this is a meeting that we had down at Function where we analyzed that. And Angus MacLean, who was a directing animator on WALL-E, looked at that, and he thought he had some suggestions for how it could be modified so that the head and neck would move more like the real character from the film. And so we incorporated Angus's ideas and a lot of changes that came from finding difficulties with the initial prototype. And the resulting pieces were fabricated in the Far East and off there, milled, came back, and then this jigsaw puzzle was assembled as rapidly as we could. Here you see the head and neck assembly operating under servo control for the very first time. And then we put together a hand assembly, which you see here, holding itself up again for the very first time. And then after this, a whole large set of miracles occurred. And eventually our character, WALL-E, was on the set of Extra and eventually touring the world, doing a wide variety of performances in support of the marketing of the film. So my part in this was the show, to figure out what WALL-E was going to do, how his motors were going to be controlled, how we were going to combine puppeted motion under control of an operator and pre-computed motions that were created by animators, combine those hopefully seamlessly to create a compelling performance.